Let's use z-scores to find probability. Part 2. A particular brand of tires lasts an average of 40,000 miles, with a standard deviation of 3,000. What is the probability a tire selected at random lasts more than 42,000? So I know my value is 42,000. If we think through this graphically, okay, so I know my average is 40,000. My value is 42,000, so it's going to be somewhere over here. We would have the probability more than 42. I'm looking at the area over here. Now, when you do this, you're like, well, this is where you need to think, I need a z-score. Because if I have a z-score, then I can find probability, right? A z-score leads to probability. How do I find my z-score? Z equals value minus the mean over the standard deviation. So 42,000 minus 40,000 divided by 3,000. We do our numerator first. 42,000 minus 40,000 is 2,000. 2,000 divided by 3,000 gives me 0.666. Keeps going. Well, if you look at your table, the closest table that we have in the table is 0.65. So we're going to use a z-score of 0.65. That tells us the area is 0.7422. Remember, the table gives you area to the left. So if I want area to the right, I'm going to take 1 minus 0.7422 for an area or a probability of 0.2578 or 25.78%. That is the probability that a tire will last more than 42,000 miles. At birth, baby weighs an average of 3.39 kilograms with a standard deviation of 0.55 kilograms. What is the probability a baby selected at random weighs more than 10 pounds? Well, we can do this one of two ways. We can either convert kilograms to pounds or pounds to kilograms. Since I already have these two in kilograms, I'm going to go ahead and change 10 pounds to kilograms. So I take my 10 pounds, I multiply by the 1 pound in the denominator and 0.4536 kilograms in the numerator, right? Dimensional analysis. That makes my pounds cancel out. So I know that my X value, the value I'm talking about, is 4.536 kilograms. We are talking about normal distribution. The average is 3.39. I'm looking at a value of 4.536, and we're talking about weighing more than that. So we're talking about the area to the right. Well, I need a z-score. So again, how do I find a z-score? X minus the mean all over the standard deviation. So 4.536 minus 3.39 all over 0.55. You do the numerator first, which gives you 1.146. Then we divide by 0.55, which gives us 2.08. Looking at our table, that is close to 2.1. So our 4.536 has a z-score of 2.1. When I look in the table, the area to the left is 0.9821. But we want this area on the right. So I'm going to take 1 minus 0.9821 and get a proportion here, or a probability of 0.0179. And that is the probability that a baby selected at random weighs more than 10 pounds. 10 pounds is a big baby. Big baby. Let's look at number 5. Friends Caleb and Marcus are comparing experiences in their first year of their respective careers. Caleb is a Boilermaker. He earned $42,000 in his first year of employment. The average salary of a Boilermaker is $63,240 with a standard deviation of $10,900. Marcus is an electrician. He earned $35,100 in his first year. The average salary for an electrician is lower at $59,190 with a standard deviation of $9,000. Use z-scores to determine which year earned the higher first year salary respective to his field. So we are looking for the larger z-score. Because we're talking about respective to his field, you can't compare an electrician to a Boilermaker. right? They're two different careers. They have two different averages and all of that. So, but if we find a z-score, z-scores can be used to kind of level the playing field. Instead of comparing apples to oranges, we change everything to pears, and then we can do it. All right, so first let's start with Caleb. We're going to find his z-score. So we need the average. The value is the amount that he's earning, 42,000, minus the average, which is 63,240, divided by the standard deviation of 10,900. When I do the numerator first, I get negative 21,240 divided by 10,900 for a z-score of negative 1.95. Then I move on to Marcus. Again, I'm finding a z-score. So how much is Marcus earning? 35,100 minus the average of 59,190 and divide by the z-score, the standard deviation of 9,000. Again, I subtract in the numerator. I get negative 24,090 divide by 9,000, which gives me a z-score of negative 2.68. They're both negative. Which one of those is a bigger number? And if negatives bother you, that's fine. There's nothing wrong with that. Think about a number line. If this is 0, as you go negative, we have negative 1, negative 2, negative 3. So Caleb is at negative 1.95, which is here. Marcus is between 2 and 3, so over here. If you're thinking about which negative number is bigger, which one is closer to 0? That's the bigger one. So we can see here that Caleb is closer to 0. So who is earning more respective to their field? That would be Caleb, because his z-score is higher. So Caleb is, I guess, the winner? I don't know, in this particular example. Okay, one more here, number 6. The average IQ score is 100 points with a standard deviation of 15. What is the probability of selecting someone at random with a score under 120? Okay, so let's think about this graphically. The average is 100. We are looking at 120. So that's to the right of the mean. So this is our piece. And we want under 120. So we're looking at all of this. Okay, great. But remember, we need a z-score in order to find the probability. So the z-score is the value minus the mean over the standard deviation. 120 minus 100 is 20. Divided by 15 gives me a z-score of 1.3333. Go to our table, and the closest is 1.3. So the area to the left is 0.9032. So there's our probability of someone having a score, IQ score, less than 120. So interpret that, right? Write a sentence. That's not what I want to say. Oh my gosh, sorry. If we choose someone at random, we have a 90.32% chance their IQ score is less than 120. That's what that means. And that is playing with z-scores, probability, and all the fun.